Let's see how to make Gauss's method easier to carry out. We're going to do that with matrices and vectors. So let's introduce matrices first. What is a matrix? Well, an m by n matrix is a rectangular array of numbers with m rows and n columns. Each number in the matrix is an entry. So matrices come in different sizes. Here's an example. This is a 2 by 3 matrix. That means it has 2 rows and 3 columns. So the first row is 1 minus 2, 3. The second row is 4 minus 5, 6. The first column is 1, 4. The second column minus 2, minus 5. The third column 3, 6. We call these numbers the entries of the matrix. For example, we use this notation. We'll use a capital letter to name matrices and the lowercase letter of the same type to indicate its entries. And we'll always put the label the row first, then the column. So this is matrix entry in row 2, column 1. So row 2, column 1 is 4. So B sub 2, 1 is 4. Okay, well, what's a vector? Well, a column vector, often just called a vector, is a matrix with just a single column. And a matrix with a single row is called a row vector. The entries of a vector are usually called components rather than entries. A column or row vector whose components are all zeros is a zero vector. Let's look at some examples. Again, we denote matrices with capital letters, and we denote vectors with lowercase letters but with over arrows, as shown here. So here's an example. Here's a vector V. It's a column vector. It has 3 components, -1, -1/2, and 0. Here's a row vector. It has 3 components also. There's no commas between the entries, -1, -1/2, and 0. This is not a vector. It's a 3 tuple. It's a list of 3 items, -1, -1/2, and 0. It has commas in it, and that's why how you can tell it's a 3 tuple rather than a vector. The difference is not just one of notation. 3 tuples are names of lists of values, whereas a vector, we're going to see that you can do things with it. It has actions involved with it. And the actions, some of these actions don't make sense for tuples. Okay, here is the 0 vector. We put the symbol for it is typically a 0 with an arrow over it, and it has all 0 entries. Okay, what are those operations we can do with vectors? Well, we can add vectors. Here's the general form of the vectors u plus v, and you can see that each one of these has n components, and we add them component by component. The sum has components u1 plus v1, u2 plus v2, u3 plus v3, down to the last component, un plus vn. We can also multiply a vector by a real number, here r. So let's take we have a real number r and the vector v, then the multiplication of the vector with a number rescales it in the sense that the number r multiplies every component. So if I take the vector v1, v2, v3 up to vn and multiply by r, I get a new vector with components r times v1, r times v2, r times v3, r times vn. Here's an example. The first vector on the left has 2 components, 1, 2, multiplied by 3, so I can multiply the 3 in to give me 3, 6, and 3 minus 0 is 3, and 2 times 3 is 6, 6 minus 2 is 4. So basically vector operations involve doing simple operations, multiplications of numbers, and additions and subtractions multiple times. Okay, let's see how to translate a linear system into a matrix or represent it as a matrix so we can make Gauss's method a little bit easier to carry out. When you're doing Gauss's method, you may have noticed that we always carry along the x's and the y's and the z's and the plus signs and the equals, and they all basically stay in the same place, and we're really just operating with the components or the entries. So what we do is we're going to just select out the coefficients of the linear combinations, but would include the 0 ones. There's essentially a plus 0y here. So you can see in this first row here, we have minus 302. Well, there's minus 302, and here we have 1, minus 2, 2, 1, minus 2, and 2, minus 1, minus 4, and 6, minus 1, minus 4, and 6. So on the left here, we have a 3 by 3 matrix of entries, and that corresponds to the 3 equations and the 3 variables over here. And then this line here is what makes it an augmented matrix. If you don't have the line, it's not augmented. This vertical bar corresponds to the equal signs. And on the right, we have the constants, minus one, that are just listed the same way. So now let's see how Gauss's method works. Well, if we wanted to, we just operate with the same notation. This adds minus 1/3 times the first row, adds 1/3 times the first row. We go all the way through all 4 entries on the first row and add it to the second row. So I've repeated the first row, and minus 3 times 1/3 is minus 1. That cancels off that. Minus 1/3 times 0 is just 0, so minus 2 doesn't change. But then 1/3 times 2 is 2/3. And 2, we have to make over that 2 we can convert that 2 to 6/3, and 6/3 plus 2/3 is 8/3. And minus 1/3 plus 5/3 is going to be 6 minus 6/3, and minus 6/3 is minus 2. Then we're going to do the same thing of add minus 1/3 times the first row to the third row, and that's going to cancel off this term. It's not going to change the minus 4 because of this 0. And then we're going to have 6 minus 2/3. Well, that's going to be 18/3 minus 2/3 is 16/3. And then we're going to add minus 1/3. Well, it would actually be plus 1/3. So plus 1/3 and plus minus 13/3 is minus 12/3, which is minus 4. Okay. So in going from here to here, you don't have to do as much writing. You don't have to write down the equal sign and the pluses. Well, let's continue and see what happens. Well, this isn't quite an echelon form because we have zeros here. We need to get rid of this minus 4. So we can perform the row operation of adding minus 2 times the second row to the last row. And that's going to give us minus 2 times minus 2 is 4. 4 plus 4 is 0. Minus 2 times this is going to give minus 16/3. We'll get 0. And minus 2 times minus 2 is 4. So we get a 0 row. Now, so this is now the echelon form in the augmented, an echelon form representation of the transformed linear system. And to solve this or to make progress, we have to translate back to equations. So we take the non-zero rows and see that this second row here corresponds to this equation here, minus 2y, because this is the x, the y, the z column, minus 2y plus 8/3 z equals minus 2. And the first row produces this equation on the left, minus 3x plus 2z equals minus 1. So we're going to repeat those equations in the next page. We have the first row and the second row. So these are our equations we get for the row echelon system. And we will see that there's a free, if we go back, we can see that in echelon form, there's a free variable. X is a leading variable, Y is a leading variable, but Z is the free variable. Okay, so we're going to parameterize these equations in terms of Z, the leading variables in terms of the free variable. And solving this equation for Z, we get X equals 1/3 plus 2/3 Z, and Y is going to equal, the 2 will cancel, and we'll end up with Y equals 1 plus 2/3 Z. And we include the Z equals Z for the free variable. So we have now sort of X, Y, Z and an expression for each of these. So we're used to writing this, so we've seen that we can write this in parameterized form as take the x expression, put it here, take the y expression, put it in the second slot, and take the z and put it in the third slot. So, but we want to convert this and write it as a vector. Okay, so I've repeated the parameterized form, and this has elements. The elements, this enables you to write the solution, each solution in vector notation. So here's the x, y, z for x, y, and z. And you can see the coefficients here, 1/3, 2/3, 2/3 are on the top row. So x equals 1/3 plus 2/3 z, 1/3 plus 2/3 z. Y equals 1 plus 4/3 z. Well, there's the 1 plus 4/3 z. Z equals 0 plus 1z. Well, that's the z equals z. So this form here collects all the coefficients, the constants, and collects the coefficients of z. So it's easy to see what happens when you choose a value for z. And here's the solution set form, in which it's just the same expression. If you're writing the solution set, we know that this order here, x, y, z, is the same as the order x, y, z in the linear system. And again, it's a nice form because z is unrestricted, and this enables us to, will enable us to understand more clearly the general pattern of solutions in that are produced by Gauss's method. Okay, and here's just an example of each solution vector. It gives you put in different values of z, and you get out different, right away, different solutions. Okay.